This week of information is going to be about what's called geometric optics. Um, and that we're not going to do anything if you looked in your textbook. And again, there's nothing in any of the things that we're supposed to cover this semester that included wave optics. It's perfectly important, but there's only so much time, so we're not going to end up covering any of that. What we will begin with is one of the oldest observations that still is perfectly good. It was observed about 2,300 years ago, and that it still is true. First of all, light will end up traveling pretty in a straight line. So there's technicalities with a straight line. If you're curious, you can ask offline. But for our purposes, it travels in a perfectly straight line. And so what happens whenever a ray of light hits a mirror? What'll happen is it'll come in, hit the mirror, and bounce back off. And the way that it bounces off will end up being such that the angle relative to the normal, remember perpendicular to the surface, the angle between the light coming in and the normal, that angle is called the angle of incidence. It's there. And then the angle from the normal to where it transmits is called the angle of reflection. And Archimedes ended up seeing that the angle of incidence was equal to the angle of reflection. And again, remember it is relative to the normal to the surface, and we'll end up seeing why that will end up being of some importance later. But it's, again, a simple geometric relationship. I will end up having a problem for you to see how we can end up doing something with just a flat mirror. It's not totally trivial. It's still going to be pretty easy, but you'll get a chance to do something exploring that. More complicated scenario is whenever we have what's called a spherical mirror. And a spherical mirror is, again, from the name, you'd expect it has something to do with a sphere. And there's two ways you can get to a spherical mirror surface. One of them is if you end up having a sphere and then you just chop it through, all the way through, and you end up taking a piece out of that. What you'd end up then having is one side that's flat, and this would be where the side that's the behind the mirror side. Then the side that's in front of the mirror will end up being out this way. That type of a mirror is called a convex mirror, and so that's one of our two varieties. The other one, if you imagine something like, you think about some soft concrete. You end up taking a sphere, you push it down into the soft concrete, and you lift it up. Then it'll leave, the depression shape of the surface. And then if you took that as being your new surface, that will end up being another type. That surface being the outer surface would describe a different type of spherical mirror, which is called a concave mirror. And that's what those two things represent. So if you have light that ends up coming from a distant location, so if you got light that's coming out of a point, it will be coming out in a straight line outward from the point in all directions. But if you end up going out far enough, you have them that they're all going out in equal directions, but if you keep moving further and further and further back, the light that ends up getting to you is closer and closer to being parallel. And you can, if you think about what's happening, then the light that's getting to you has to be almost straight on, because otherwise it would miss. It would go up here or down there or somewhere else. For it to get to you, it has to almost be coming straight at you. So a distant light source is what we're looking at whenever we're trying to understand what a focal length is. So if we've got very distant light that comes into a convex surface, then on the sides of a convex surface, remember the normal has to do with the tangent plane. It's perpendicular to the tangent plane. So whenever you end up having a ray of light that ends up coming in, say up at the top toward, doing this with a, so if it comes in like this, then it will end up, the plane will be here, the tangent plane. So then the normal will end up bending it out from there. So the light would end up bending outward from the curved surface. So then the light would end up coming in directions out like this. So if you're looking at it from a distance back here, that we said that light that comes from a source ends up going out in all directions from a point. So in order to find where that appears to be when you look in the mirror, you keep on tracing back behind the mirror until they end up coming together to a point. And that point, that distant light would end up giving you is where the light seems to be coming from on the other side. That's called the focal length, the focal point. And the focal length is the distance from the front end of the lens to where that happens back behind the lens. And because for a convex mirror it is behind the lens, we end up saying the focal length is negative because it's in the direction that the light actually can't be. The light is not literally behind the mirror, of course. The light is only in front of the mirror, but that it looks like is coming from behind the mirror. So its effective point is behind the mirror. For a concave mirror, on the other hand, when light ends up coming in, that the light will end up coming in, and the surface here, tangent, will be this way, so it ends up bending in. So then the light rays that come in come together to a point in front of the mirror. So the distance from the front edge of the mirror to where that is, that's also called the focal length of the concave lens, but it's positive because it's a location where the light actually can be. So the light can't be back here behind it because it doesn't go there. There's nothing back there, but that it looks like it's coming from back there. So that's what we're talking about with these. So a negative focal length, it corresponds to a convex lens, and that it will be again behind the mirror, and the focal length of a concave mirror will be positive. It will be in front of the mirror. It's where those light rays appear to be coming from. Finally, in terms of geometry, we can relate what those focal lengths are to the original sphere that we sort of took it from. It turns out, and the geometry is painful, so I'm not going to try to do it on there. I think your text may end up trying to show it to you, but it is just ugly painful to end up doing all the geometry. But it turns out that the focal length ends up being plus or minus half the radius of that original sphere. So you can just take that on faith, because I don't want to end up trying to explicitly prove it.